Structural dynamics is the study of motion. Under dynamic loads, engineers need to know exactly how a beam bends, vibrates, and reacts over time. This global equation adds the mass matrix times acceleration to the stiffness matrix times displacement, equating to forces plus support reactions. Expanded into massive 8x8 grids, it mixes unknown node movements with unknown support forces. This creates an unsolvable, singular system. To break this deadlock, we rely on the physical environment. Geometric boundary conditions act as the required mathematical triggers to partition this singular matrix into components we can actually compute. Consider a cantilever beam rigidly embedded into a concrete wall. The free end undergoes heavy vibration, but the connection at the wall remains perfectly static. This diagram translates physical reality into mathematical axioms. At the fixed wall, node 1, displacement is 0 and slope is exactly 0. Because position and slope never change, their second time derivatives must also be exactly 0. Acceleration is 0. We can now return to our unreduced 8x8 global matrix to execute the necessary matrix surgery. We insert these new constraints directly into the acceleration and displacement vectors, replacing the variables in the first two rows with absolute zeros. The mechanics of matrix multiplication dictate that multiplying a matrix by a vector containing zeros completely nullifies the corresponding columns. Based on those zeros, we strike through column 1 and column 2 in both the global mass and stiffness matrices, dropping them entirely. Enforcing zero displacement constraints surgically removes specific columns from the system's influence, stripping away the singular nature of the global matrix entirely. With those columns deactivated, we shift our analytical focus to the remaining active rows. Rows 3 through 8 represent the free nodes of the beam, nodes 2 and 3. In these specific rows, the external applied forces are strictly known quantities. This leaves structural displacements as the only unknowns. We physically extract these active rows to form a completely independent mathematical system. This newly extracted 6x6 block forms our primary equations. These equations are strictly solvable. Using numerical techniques, we calculate the time response for the unknown displacements and slopes. Next, we direct our attention back to the rows that were left behind during the extraction. In rows 1 and 2, the node displacements are permanently set to 0, but the physical support reactions remain entirely unknown. We extract these two rows into their own discrete mathematical block. These form the secondary or auxiliary equations. This sets up a precise operational loop. The kinematic data solved in the primary equations is routed directly into the secondary equations. This final substitution reveals the actual physical forces occurring at the beam's supports. To verify this mathematical procedure applies to all boundaries, we test it against a simply supported beam, pinned at both its left and right ends. Pin joints possess unique mathematical constraints. The vertical displacements are 0, but the angular slopes are permitted to rotate freely. Mapping these boundary constraints into the displacement vectors places our zeros exclusively at entry 1 and entry 5. Because these zeros are non-adjacent, they dictate a distinctly different matrix surgery pattern. We eliminate column 1 and column 5 across the global mass and stiffness matrices. Unlike the cantilever case, this reduction forms a checkerboard pattern. The extracted rows weave together non-adjacent data points. These rows condense to form the primary equations for the simply supported beam. The skipped rows are then extracted to form the secondary equations, containing the unknown pinned support reactions. While altering the physical geometry drastically alters the visual extraction pattern, the exact same rigid mathematical partitioning rules dictate the survival of the variables. This empty flowchart represents the analytical workflow, allowing us to step back from intense matrix operations. Step 1 is the generation of unreduced singular global mass and stiffness matrices. Step 2 introduces physical boundaries as numerical zeros to execute matrix surgery on unnated columns. Step 3 extracts the free rows to form and solve the primary equations. Step 4 routes that kinematic data back into the constrained rows to solve the secondary equations for support forces. At this point, the mathematical foundation is set. We can look forward to the next stage of finite element analysis, applying time integration numerical methods to these partitioned matrices. Geometric boundary conditions are the mathematical sorting mechanism that translates theoretical physical systems into functional, computable structural dynamics algorithms.